Welcome back, everyone. We're doing one more theoretical video on roots finding algorithms. This will be the last one for this. Next video is going to be a screen cap off my laptop. We'll get to see all these root finding algorithms in practice and implementation. We've already done the bisection method. We've already done Newton-Raphson. What we're going to do today, we're going to do Newton-Raphson for a system of equations. So when I say a system of equations, what we mean, we no longer have a single equation, we have several equations. So let's say that we have an equation f and we have an equation g. Now we have two different functions, which means we need two different variables. So here is f of xy, here is g of xy, and we are still looking for the roots. Right? We still want to know where these algorithms are evaluated at 0. We want to know the values of x and y that are going to make these functions equal 0. Okay, let's do the theory for this, and then we'll do the pseudocode. Let's cook up an algorithm for the Newton-Raphson for a system of equations. We're going to do this. We're going to derive the approach using a Taylor series expansion. Okay. Remember that we have two functions. We have f of x and y, and we have a second function g of x, y. And let's write out the expansion for these. Now consider each of these functions have multiple input variables. So this Taylor series expansion we're going to do, it's specifically the one for multivariate functions. So this expansion f of x, this is going to be the function f evaluated at some initial points, x naught, y naught. And then we're going to take partial derivative of f with respect to x. We're going to evaluate that at x naught, y naught. We're going to multiply this by x minus x naught. So here's the derivative of f with respect to the variable x. So there's your partial derivative. We need to do the same thing for f now with respect to all the other variables. So in this case, we need to do it with respect to y. So let's add partial f, partial y. We're going to evaluate this again at this initial point, x naught, y naught. And we're now going to multiply by y minus y naught. And then I'm going to say plus dot, dot, dot. I'm going to put an ellipsis at the end. And this ellipsis represents higher order terms, higher order derivatives. So here is the 0th derivative, here's the first derivative, second, third, fourth derivative, and on through that infinite series. If you were to include all of these infinite terms, then this is an actual equals. We are going to truncate it. We're going to make it an approximation in just a moment. Next, let's write out the same expansion for g. So g is going to be, here's the function g evaluated at x naught, y naught. Let's go through the two derivatives. So partial of g, partial of x, evaluated at these points, multiplied by x minus x naught, second derivative now, partial with respect to y, evaluated at these points, y minus y naught, plus dot, dot, dot. Okay. So what are we going to do with all this? We would like to take this and we would like to make this expansion. Hey, honey, come on. Yep, there you go. Okay, so we have this now. We need to take this and rearrange it into some kind of iterative update step. Remember when we did Newton-Raphson for a single function, we used the point slope form and we used that to solve for an updated x value. Let's see what we can do with this. I'm going to take these functions here on the left, I'm going to put them in a vector. So this vector is now going to contain f and g. If you remember, this is a roots finding algorithm. We want to know where the functions themselves are equal to 0. So I'm going to say that f and g are equal to 0. Next, this is an equal sign because it's an infinite series. We're going to truncate the series, which will make this be approximately equal to. Next, I'm going to take the original functions. I'm going to bring those down. I'm going to put those inside of a vector as well. So here's f of x naught, y naught. Here's g of x naught, y naught. Next, we need to do something now with all of these derivatives. So to help us out, I'm going to draw some brackets around them. Let's think of them this way. There's 2 functions, 2 unknowns, which makes it a 2 by 2. And notice that we could factor out this x minus x naught and the y minus y naught. We could factor those out to the right. If you do factor those out and you extract them from the equations, that's going to take what's inside the braces, and that's going to leave that as a matrix. So here is partial f, partial x. Here is partial f, partial y, partial f. Sorry, not partial f anymore. Now it's partial g, partial x, and partial g, partial y. There's those partial derivatives. You take this entire 2 by 2 or n by n matrix, and you evaluate this matrix at those given points, x naught, y naught. We then multiply by these extracted portions. So there's an x minus x naught here, y minus y naught there. Okay, next, we have this is literally just these equations truncated. We put in the approximation, and then we have written it in a linear form, or we're starting to write it in a linear form so that we can keep it organized. Next, let me make sure you get this in your notes. Let me clean this up, and we're going to move on. I've rewritten it just kind of in this simplified form so we can look at it for a moment. What I want to do now is let's talk a little bit about this nomenclature. I said that there's functions f and functions g. There's variable x and variable y. What if we had 50 functions and 50 unknowns? We don't want to call them functions f, g, h, I, etc. We don't want variables x, y, z, x, y, y, z, z, something. Consider that we want to expand this for n number of dimensions. In that case, let's relabel a little bit of this. Let's say that these functions, the functions are now f1, f2, f3, dot, dot, dot. And then these are functions of variables x1, x2, x3, dot, dot, dot. What that means is we can have n number of functions, and they are the functions themselves have n number of variables. So what's the proper way to write this system then? We could express the entire system just by writing f of x. Now, if this was in a textbook or a paper, we could use the word processor to make these bold to show that these are vectors. We could also put a bar over each of these to show that this is a vector of functions. This is a vector of variables x. So from now on, let's talk about this system only in terms of f and x. Just understand that f and x themselves are both vectors. This is still fundamentally the same thing. We're just thinking of all of these terms themselves as vectors. An interesting point, and this is just for your familiarity with the math. Recognize that this matrix then is the derivative of a vector with respect to a vector. which ends up being a matrix. So let's rewrite this now. I'm no longer going to use the curly braces. I'm just going to call this on the left-hand side 0. And if you wanted to, oh, that's a terrible 0. There. If you wanted to, you could, in your notes, also put bar over this to denote that it's a vector. I get tired of using bars. So I'm just going to write it as 0, remembering that this 0 represents a whole vector of zeros. So 0 is equal to, here is the function f evaluated at the variables x, again, vectors, plus, and then this matrix right here, if you take a whole series of partial derivatives and you put them into a matrix, that matrix actually has a name. It's called a Jacobian, and we're going to use the letter J. So again, this matrix right here, this is called a Jacobian. So it's a Jacobian matrix. You build and you evaluate the Jacobian matrix, that's right here, and that is J, and we're going to take J, and then we're going to multiply by x minus x naught. So again, that was just simplification. These are the exact same things. All we've done is we've taken this and we've cleaned it up just a little. Remember that this is not a function call. This J by itself is a matrix. It has dimensions n by n. It's a square matrix where n is the number of functions and also the number of inputs. Okay, good. Given this, we can use this now to come up with a very nice iterative algorithm. I'm going to clean this up and let's talk about that. Okay, here's that same equation. All we want to do is we want to use this equation to solve for an update, right? We're doing a Newton-Raphson, it's an iterative thing. We want to find a new value. So given some inputs, x naught, we actually want to solve for x. This would be the updated value of x. So we need to manipulate this equation to find that variable. Clearly we can take this and move it to the other side. I can say, let's say that j times x minus x naught. We can say that this is equal to minus f of x naught. We want to get x by itself. And this j is a matrix, so you can't divide by j, but you can do an inverse. We can say that x minus x naught is equal to negative. So here's the inverse of j multiplied by f of x naught. And now we just want x. So x equals x naught minus j inverse f of x naught. And there is your Newton-Raphson for a system derived using a Taylor series expansion. Now, this may not look like our update steps that we did from the previous algorithm, so let me make a small change. Here is x, n plus 1. This one is x of n. This one is x of n. So, given some vector of inputs, given some knowledge of a function or system of functions, and then if you know the functions, you can evaluate the partial derivatives and you can build this Jacobian matrix. You invert the Jacobian matrix, you multiply by f of x, and then you subtract that quantity from x in, and that is now your update step. So again, this is for multiple functions. Let's do not a full example, but I'm going to show you how to build this Jacobian function matrix if you're not particularly familiar with partial derivatives. I have an example to show you that. And then we're going to have another video in the next day or two with implementing this. But let's go ahead and do the worked example. Okay, let's say our first function, f, let's do f of xy. Let's say that this is equal to x cubed plus y squared minus 1. And then we have a second function g of xy, and that one is equal to x times y minus 1/2. Here's your original function. This is the information that you have. Let's say you want to write a Newton-Raphson algorithm that's going to solve this system. We need to construct a Jacobian matrix. We said this Jacobian matrix is partial derivatives. So partial f, partial x, partial f, partial y, partial g, partial x, and then partial g, partial y. This symbol that I'm using, by the way, if you haven't seen this before, it's like a cursive D. So, what are these partial derivatives? Again, if you're not really familiar with partial derivatives, what we're going to do, if I say partial of f with respect to x, that means take the function f and then take the derivative of it with respect to this variable x and then hold everything else constant. So we know, for example, that y is a variable. When I'm doing partial f with respect to x, I'm going to treat y as if it's constant. When I get to here and do partial f, partial y, I'm going to treat x like it's a constant. Okay, so partial f with respect to x. Well, here's the equation, right? Just analytically take the derivative of it, and we will get 3x squared. Next, partial f with respect to y. We're treating x like a constant, -1 is a constant. This yields 2y. Partial g with respect to x is going to yield a y. And then partial g with respect to y is going to yield an x. Okay. Notice that it doesn't matter what the values of x and y are. These are always the partial derivatives. So in your code, when you're working these problems, you can write a function call for the Jacobian. You pass it values of x and y, and it returns the matrix of numbers. Let's just suppose that at a certain point, x and y is equal to 4 and 5. You have a function call for the Jacobian. You pass it the values 4 and 5. It's going to return, excuse me, so 3x squared, that's what, 16, 32, 48. 2 times y is going to be 10. Next, this is just going to return y, that's going to be 5. And then this is going to return x, and x is 4. And there we go. That is the Jacobian for this system of equations evaluated at the points 4 and 5. So again, you should be able to do this. You should be able to do this just as a function call. Okay. Given all this, I expect that you can. I'm expecting you're going to be able to find these partial derivatives and build this Jacobian. Let's write out the pseudocode for this algorithm and we'll be done. Let's do the pseudocode. Number 1, remember the user has to provide some input. So the user inputs initial conditions or initial guess, let's say. An initial guess, and I'm going to call this x naught. And I'll put the bar over it here, just as a reminder, we're dealing with a system of equations. So if there are 10 variables, if there are 10 x's, you have to provide an initial guess for all 10. Next, number 2, we want to perform a check. Check that remember when we did Newton-Raphson, we checked that the slope was not equal to 0, right? Because this was part of the update step. what we're doing now for a system is we're performing matrix inversion on the Jacobian. And this is the system counterpart to that same operation. So we need to confirm that this inversion can take place. For matrix inversion, we can do that. We can check that the determinant of the Jacobian is not 0. And if the determinant is not 0, that means the matrix is invertible, so we can perform the update. So we perform this check. Next, let's set x2, and again, we're dealing with vectors here, so x2 is a vector. X2 is going to equal x1 minus j inverse f of x1. So the x1 here, at step number 1, I said input some initial guess, x naught. Clearly for the first round, x1 is equal to x naught. Next, for we're going to set x1 equal to x2. We've seen this before. This is just taking this updated value and overwriting x1 such that the previous step 3 can be run in a loop iteratively. In fact, just to make that a little more clear, I'm actually going to back up here. I'm going to say that this is J. This is the Jacobian of x1 does not equal 0. Because remember, every time the x's change, you need to recalculate the Jacobian, and you have to confirm that the Jacobian is still invertible. Next, 5. We're going to repeat this process. We're going to repeat steps 2, 3, 4. Until what? Recall that in previous algorithms, we have set some convergence threshold on this. We're going to do the same thing here. Let's say until x1 minus x2. So these are the updates. At step number 4, before you perform this overwrite, before you lose the data on the previous values, go ahead and perform this check here. So we want to perform x1 minus x2, but remember that these are vectors. So really what we want is the norm of the vector. The norm is going to take into account all of the errors. So if I double bar this, and tell you what, I'll even just write this out. We're looking at the norm of this vector. So that would take it down to a scalar. We want this norm to be less than some very small number. Here's our specified threshold. Or what? We could say or f of x, x1, x2, this could exactly equal 0, which means congratulations, you found your roots. But really, the other or we're worried about, or if your number of iterations has exceeded some maximum number of iterations. So again, we've seen all of this on the previous algorithms. If you have your bisection and Newton-Raphson up and running, this will make sense to you. Okay, so that's it for today. Here's your pseudocode for Newton-Raphson for a system. Keep an eye out for the next couple of videos. We'll be looking at all of these algorithms, implementations of them. We'll see them live running. And then after that, we're on to a new topic. So as always, stay safe, wash your hands, and I'll see you next time.